All right. So just to back up a little bit and remind you of our formula that we are going to use. It's still statistic minus our whatever our value of the null hypothesis is over the standard deviation. Right? T-score is going to be very similar to Z-score there, where we have our value minus our mean over standard deviation. And so we're going to use that. We're going to bring back our degrees of freedom, being our sample size minus 1. And we're going to have our conditions, which is what you saw flashing up there. All right, so we have our data in list 1. There's your null and alternative. And the way that you know that is the null and alternative is because it says an oxygen level below 5 puts life at risk. So our null is that mu is 5, and our alternative is that mu is less than 5, because that's what we're interested in. We're interested in, is the oxygen level below the 5 milligrams per liter? So that's what we're interested in seeing. Is it too low at the very low value? So this is going to be a one sample t-test. And we are going to check our conditions here. So conditions we're wanting to check are still random, normal, and independent. Random, well, we have 15 randomly chosen locations along the stream. Normal, we're checking if the sample size is at least 30. And so here the sample size is not at least 30, so we need to investigate further and see if we have any evidence to overturn a normal distribution. Again, the big things that you can check for here are my box plot should be fairly symmetric. And this one, the normal probability plot, should be fairly linear. Since we have that data in our calculator, we can actually make those. If I went over to second and our stat plot, then I could plot list 1 to make the box plot. You would select this option. To make the normal probability plot, you're going to select this option over on the far right. So those two things those two places are where you're going to look. And in this case, we don't see any evidence that is really enough to overturn it. Normal probability plot looks fairly linear. Box plot looks fairly symmetric. So we are clear to use a normal distribution. Remember, if n is bigger than 30, then we don't need to check any of this. We can just say n is at least 30, so we have our normal distribution. And then independence, how many different, randomly chosen locations and samples of water could we take? Well, basically infinite, certainly greater than 150. So that would be our independence condition. Or we could say that each of these samples, samples of water in the river are independent. So I'll leave that up there for just a moment. It's going away in about 30 seconds. All right, step 3, we need to do our calculations. So this is where if you did one variable stats, that's going to be useful because then you're going to know what to plug in for all the values here. And if you did those one variable stats, you would see that here's the mean, here's the standard deviation. So again, our formula is going to be the value, which is x bar, minus the mean. Well, the mean in the null hypothesis is going to be that it was 5. Over our standard deviation is going to be s of x over square root of n. Boom. And notice that here we get a negative t-score. We get a negative t-score because, you'll see this diagram in just a second, you're getting a negative t-score here because we are looking for it to be less, whether it's less than 5. And so since we're looking for less than, that means we want to see how low. And so it should be below the mean, negative t-score. And so the probability we're trying to find should match the alternative hypothesis. Since the alternative hypothesis was that we were less than 5, then we want to find the probability with t-scores that we are less than that value. You should write down, here's the things you need to write down. You need to write down the formula, plug in the numbers, answer. So getting this t-score of negative 0.94. You should write down the degrees of freedom is 14. And then you should write down your p-value. We'll go ahead and write down our step 4 and our conclusion. You do not need to show the entire picture and the table and all that in step 3. Because most of us, we're not going to use the table, we're just going to use the calculator. And the p-value, we'll get the exact number out, but it is greater than 0.05. So since p-value is greater than 0.05, that means we are going to fail to reject, and that means we don't have enough evidence for our alternative. So it's the same process that we've been doing the last few days. The only difference is that we're using the t-score in that formula instead of a z-score formula. And when we check our normal, and we need to think about degrees of freedom, then when we check our normal condition, we need to think about n being at least 30 instead of our n times p and our n times 1 minus p. Kind of the same differences that we had when we did means versus proportions for confidence intervals. But we're going to have that same 4-step process with all the same ideas. Now, I want to shift into talking about the calculator here. So your data should be in list 1 on the calculator. And we're going to go to stat tests. Under stat tests, we are going to use a t-test here. So one sample t-test. And it's going to ask, do you have some stats to give me, or do you have some data that's in list 1 that I can use? Well, I have some data that's in list 1 that you can use, calculator. So I'm going to tell you that the null hypothesis was that the mean was 5. I'm going to tell you the data's in list 1. I'm going to tell you that the alternative was that the mean was less than 5. And I'm going to ask you to calculate it. There's your t-score. There's your p-value, 0.18, which was greater than the 0.05. There's your mean. There's your standard deviation. And there's your sample size of 15. So degrees of freedom was 15 minus 1, which is 14. So t-test is the place that you go in the calculator. In this case, you had data in list 1, so you're telling it to use list 1. And then it'll tell you what the mean and standard deviation and all the numbers that you need are.
Mr. Hoffman, I have a quick question.
Sure.
So, do we list the degrees of freedoms just to have it listed that we know what it is, or do we? Is that significant in our use for our calculator? Like, do we have to put 14 in anywhere, or do we just want to list it in that step just to say that we know what it is?
You are listing it in the step just to say that you know what it is. So in other words, the calculator, will do the degrees of freedom stuff for you. But for the grading of step 3, one of the things they're going to be looking for is that you listed the degrees of freedom.
Okay, sounds good. Thank you.
So you'll need to say degrees of freedom is 15 minus 1, which is 14. Other questions?
So I was getting the numbers in the L1. What is the frequency? What do you put in for the or whatever?
You shouldn't need to touch the frequency section of it.
Gotcha.
Other questions? I had a couple of people who said they were unsure, and so hopefully now that we've seen gone through the whole problem, it's making a bit more sense. It's coming together a bit better. If not, we'll do one more, so you'll see it again. All right, you don't need to write this part down, but I just want to point out that if we're failing to reject, remember that when we talk about type 1 and type 2 error, failing to reject incorrectly is a type 2 error. So if we are making the wrong conclusion here, then we are making a type 2 error. In other words, we are saying there's not enough evidence that the stream is less than 5 when in fact it actually is. That's the error we'd be committing. We'd be saying that the water's safe when it's actually not. So just to point out that that type of error would be there. Okay, I'm going to move on. I want to look at the next problem, but I actually want to give you about 10 minutes. And I want you to see how far you can get in the 4-step process before we actually do the 4-step process here. Oh, actually, no, I lied. There's something we need to do first. I forgot. This is a review question that it's asking here. We have the random sample. We have that, summarizes the data, determine whether there are any outliers. So this was something we did all the way back in chapter 1. So I just want to kind of review this idea of testing for outliers, because it's been a while since we've done it. Our test for that is to use 1.5 times interquartile range. So that means we need to find our interquartile range. Let's see where it is. There's our Q1 and Q3, so we're going to subtract them. That's our interquartile range. So take Q3 and add that 1.5 times the interquartile range. Take Q1, subtract the 1.5 times the interquartile range. Those are our boundaries. Anything above the top or anything below the bottom is an outlier. So there's Q3. I'm going to add that 1.5 times IQR. I get 40.3025. I'm going to take Q1, 29.99, and subtract 1.5 times IQR, and I get 23.3. So anything above 40.3, anything below 23 is an outlier. And we don't have any values that are outside of those boundaries. So we have no outliers. Okay, now let's read the problem. And now I'm going to give you about 10 minutes. And I want you to get as far into the 4-step process on this as you can. Figure out what your null and alternative are going to be. Check your conditions. See if you can set up your formula. So 10 minutes, give it a try. Key words in the problem that we are doing, aside from the header of two-sided tests. Keywords in the problem that we are doing two-sided test would be, the managers are wondering whether this change will affect the mean weight of future pineapples grown in the field. So we are saying, will it affect it? Will it make a difference? Doesn't say whether the difference is in any particular direction or not. It's just saying, is it going to change? So that's a two-sided test. So if we're doing our null and alternative, our null should be that the mean is 41, and our alternative should be that the mean is not 41, and then we should define what our variable is. And we're using alpha as 0.05. That's our step 1. Step 2, it's a one-sample t-test. Checking our conditions. We took a random sample of 50. Normal, good news, n was greater than 30. So we don't have to check anything else. We can just say our sample size is at least 30, so we can use approximately normal distribution. Independent, there need to be at least 500 pineapples in the field. If there's a large field, then we can accept that. 10 seconds, this is going away. And we're moving on to step 3. All right, I'm going to be showing the calculator here. we're going to go over to stat tests. And it's going to be a t-test. So this time, you are going to tell it that instead of the data, pull it from list 1, you're going to tell it, I have some stats to give you. And it's going to go, great, what stats do you have to give me? The null hypothesis was that the mean is 31. X bar, well, let's read out the table. Let's see. Our mean here was 31.935. It gave the standard deviation. Standard deviation was 2.394. Our sample size was 50. So you should also be putting degrees of freedom being 50 minus 1, which is 49. Our alternative was that the mean is not 31. So not equal to. So that's what it should look like. You're going to put your mean standard deviation there. You're going to put your sample size. And our alternative, it's a two-sided test, so we're going to put not equal to. Calculate. There's our t-score and our p-value. So that's the calculator. So here's what you're going to write down. Formula, plug in the numbers, answer. And remember, the tail that you're finding, if you're drawing a picture of the t-score and the tail that you're finding should match the alternative. So last time, our alternative was that the mean was less than an amount, and so we used the left tail. This time, the alternative is the mean is not equal to an amount. So we're looking in both directions. So our diagram that we're about to draw is going to have both tails in it. And yes, the p-value is 0.00. It gives it in the calculator. 0.00807, so 0.0081. And guess what? That value is less than our alpha level, which means we are going to reject our null hypothesis and say there is enough evidence for our alternative. Reject the null hypothesis and conclude, what was the alternative? The alternative is that the mean is not 31. Again, make sure you write degrees of freedom. Degrees of freedom is 50 minus 1, which is 49. And then you can write your p-value. So something to remember, I'm going to talk broadly about what the next two slides are going to say. And I'll show the next two slides. Remember, this does not say what the mean is. We just know that we have evidence to say that the mean is not 31 anymore. It doesn't say what direction it is. If we want an estimate of what the mean actually is, that's the information that confidence intervals are going to give us. That's information that's going to be useful in a confidence interval. And if I were to do the confidence interval, by the way, here's the standard error that you would use. So you'd have the t-score times our times that 0.339. Here is the 95% confidence interval. That gives me an estimate of what the new mean actually is. Notice the number that's not in that confidence interval, 31, which is what our null hypothesis said the mean was. So that leads to us rejecting that null hypothesis and saying, here's some reasonable values for the mean now. It's not 31 anymore. And in general, it says there's a link between a two-sided test at an alpha level and a 100 times 1 minus alpha % confidence interval. So in other words, since we are at an alpha level 0.05, this tells us information about the 95% confidence interval. alpha level 0.1 tells us about the 90% confidence interval, and so on. So it's kind of like the inverses of each other as to what the confidence interval tells us. And that's for two-sided tests, because the hypothesis test is going to tell us about the tails. The confidence interval is going to tell me about the middle values, about the middle 95% of the data. And then the hypothesis test is interested in the 5% of the tails. So this tells me that information again, that we can, to determine whether we reject or fail to reject the null hypothesis, we can look at the 95% confidence interval and see, is the null hypothesis in that interval? So when we said 31 was not in that confidence interval, then that could lead us to say, oh, that means we're going to reject our two-sided null hypothesis.